Okay. Good. Okay. So I guess now you see also, okay, but this is the elevator pitch, it's not what I want to show now. This we keep it for later. This is the things that we start with. So 3 minutes and then we start. Mostly because the beginning is just an introduction, so there's not that much like work to do.
Her name? Her name?
Yeah, you can see it here. Mariam Fami. She's well, she will present herself later as well as you all, but yeah, she's working in Galway. She's also a PhD student.
Where are you now, Mariam?
I'm in Galway and UIG.
Is in Ireland, and she works in the same group of well, in the same European project as Pavle in our group, and so that's why she joined today, because she may also do some DFT at one point.
Okay.
But she's not Noria's group.
No. I mean, no. So the point is that in all these European projects, what you usually do is that you travel in different places. Are you supposed to come to SAQ, Mario?
Yes,
Okay, then it makes sense. Yeah, so she
this
will
is pretty interesting.
at one point. Yeah.
Okay.
Yeah, but it's also true that, you know, with this COVID, no, but now it's getting better. So
Yes.
people should come, you know. Okay. Maybe I lower a bit the temperature because I feel like that the air conditioning already stopped. So there is an auto. Yeah, because it's 24.
Maybe just reach the temperature.
Yeah, I think so, but you know, like, yeah, we can put it 23.
Oh,
I mean, then if it's cold, then we rise the temperature.
Yeah.
But I don't think it is really 23 inside. So let's make sure that Santiago know the place, and then we start.
he's not here. I think we.
No, he had a meeting in the bank. That's why he told me that he
Okay.
may be late. But I just like want to make sure, you know, because then if later he send us an email or call me, like we don't see.
Okay.
Well, yeah, he sent him an email. So I think we can slowly start. Okay. So, welcome here, all of you. I mean, we are really few, so it's really a familiar meeting. You know, it's not a online class. So this is a crash course as I wrote. So don't expect me to teach all the DFT because I don't know myself. What is important for you also, depending on what you need to do, is just to learn the best. Mostly for you, for instance, since you don't have that much time, it's not important to learn everything. You just need to learn the things that are important for you. So I'm a postdoc in the group of Nuria, as you see for this DR in front of my name, and that is my email that you already know, so you can send me like email whenever you want, okay? So I start just reminding you about the structure of the course, and just to clarify a bit like the concept, okay? So as you see here, we have like some theoretical lectures, like the one of today, that cover an introduction, or like in the other day also the correction of the exercise we do all the times, plus also the introduction to the exercise you need to do. So you have this Anson that you didn't see yet, or maybe some of you did on the VASP course, but still, like, I will give you to you today. So this will be the exercise. So let's say, like, for instance, today we start with the introduction, that is this one. Then we do some theory, really basic theory. So again, like, you will be provided with a lot of references. You have books to read if you want, you can do that. But here we will not cover everything, because otherwise this course should be like many more hours, and probably also the teacher should be better, because I mean, like, I'm not a hardcore physicist working on DFT development, okay? So just to, let's say, to specify a bit better what are lectures against tutorials. So like in the lectures, we do overview about theory and exercises you need to do. We correct the previous exercises. Of course, today we don't, because we don't have, but from Wednesday we will do. You just need to bring the notebook with you, because you just need to take note. And if you want, if you have questions, don't wait till the end. We have time, so you can just stop me at any time. We hear you, Mariam, so we will stop also if you talk, let's say, and we just discuss. because otherwise we will just sum all the question at the end and it will be a big mess. Tutorials. So the tutorials instead will be a discussion about the main problems that you have doing the exercises. So what does it mean? It means that, for instance, you will have exercises today. I will introduce them to you. You will try this afternoon, tomorrow morning. And then tomorrow at 10, you have 1 hour to ask questions. That means that if you have something that you cannot do, you can tell me, look, this I cannot do, or I have problem, I don't understand, I should do that. And then we discuss here all together. If you don't have any questions, then we meet here at 10, and at 5 past 10, we are free and we go home, or go to the office to do other things, you know? So tomorrow will not be a lecture, it's more like a discussion between us. So in that case, it's better if you bring your own laptop, because then it will be also easier for me to see where the problem is. In your case, I think it's better to connect with any desk, Sichen and Enrique, and also Santiago when you arrive. Mariam, you can use the virtual machine, now that you have also the credentials. And what is really important is that we have 1 hour, you are 4 people, so the structure will be the following. Tomorrow, like each of you will have 15 minutes maximum to discuss about potential doubt. So that means that you'd better also discuss between you two, maybe by email, like to understand, like if maybe some other people can help you with your problems. And why we put this, Santiago? Hey, don't worry, we just started. So, Mariam, so this is Santiago.
Hi, Mariam.
Hi, nice to meet you.
So he's a PhD in our group, well, in the group of Nuria since 4 months. No, don't worry, Santiago. You told me before and we just started. So as I was saying, now just relax, Santiago, take your time. We don't want to do that. So as I was saying, like different between lecture and tutorial. Like today, lecture, so theory, exercises. We correct previous exercises. You just need a notebook. And then whenever you have questions, you just stop me on the way. We don't wait till the end. Instead, tomorrow or Thursday, when we have tutorials, we discuss the main problem. You need to bring your own laptop, either with connection with any desk or virtual machine. And you have 15 minutes each to ask questions. If we finish before, because maybe you don't have questions, then it's even better. Then we finish as soon as we are all done. But the important point is that we have this maximum 15 minutes, and why I wanted to set this maximum and not to have a general conversation. Because at least to my experience in these 3 years and something of PhD, I realized that one of the main problems I had with supervisor were that I was always asking so many things that I could have asked directly to other colleagues in the group. And the problem is that usually the meeting that you have with supervisor are really short. So you really need to go straight to the point of the things where you think that the supervisor is really important. You cannot stop the supervisor to ask him, look, this comma, I don't know if it's here or here, because maybe this answer can be given by a colleague next to you. So it's much better that you talk between you work together, and then if there are things that are really impossible to all of you, then, I mean, you take my time. I mean, in my case, it's not that important because, you know, I have a lot of time, but that is mostly to prepare you when you will have, I mean, in our case, meeting with Nuria, and in your case, Mariam, meeting with your own supervisor, because usually they are very busy, so you don't have that much time. They don't have much time. Then, the materials that we will cover. So you already got a OneDrive link. I will upload everything there. We are registering these lectures and also the tutorials via Zoom. So you will also be able to see that. There is, as I said before, a detailed explanation online of what we are saying today. So don't expect me to be like too detailed here, because there is no time, and also because probably like I'm not that good in going that much in detail, because I'm saying I'm not like focused on DFT like development. But here you will get all the useful information to be able to run like simulation, or at least all the information that I found useful during my PhD. Because as I say, like I'm not a pro in VASP, but I managed to do everything I need. Here, this is the very important link, because there is a wiki page of VASP that is a manual online. So you can just go to like the search button, and then you can look everything. So if you have a tag or like something that you don't know what they are, you just look there, okay, INCAR, what is INCAR? And then, you know, you search for that, and like a page will open when they tell you, look, the INCAR is the input file where you define like the tags and all these kind of things. So save this link, and because you can do it later. Anyway, like I will provide you this slide, okay? So now we go to the nice things. So we have this elevator pitch competition that is not really a competition. just to know each other. We have around 2 minutes. Don't worry, I don't have like, I will not check the time. So, you know, if you take 2 minutes and a half, doesn't matter. Also because usually I myself very long. So I start myself and then we go in alphabetic order. So as you see, me, Enrique, then you, Mariam, then Santiago, and then the last one is Ika. Okay, alphabetic order with the name. So, and remember that whenever like, well, now I'm talking and I have the camera in front of me. Then Enrique, when you talk, then you move the camera in front of you so that Mariam can see. So as you all know, and I said before, I'm working in this project, Flow Photochem. That is a European project. There is also the supervisor of Mariam there, Pau, that is actually the coordinator of this European project. I'm doing the FT modeling of CO2 electroreduction, so it's electrocatalysis. I'm a postdoc in the group of Nuria since 9 months. In 2020, I got my PhD in chemistry in the group of Nuria, and before in 2017, I got my master in physics. So I studied physics a lot, mainly theoretical physics, and I moved to chemistry, okay? About the skills, I focus on the main one. So during the PhD, I developed a lot of data analysis, mainly through Python programming. And in order to generate the data set that I needed to analyze, I use ab initio molecular dynamics that we will briefly cover today, and you will see why ab initio is, why molecular dynamics can be used. Then I also kind of enjoy work with data visualization. So you see, like, for instance, like this like graph is done with Blender. So these are molecules, these are CO2, these are cation, these are water molecule. All these figures were done with ab initio molecular dynamics. Well, let's say the input were from ab initio molecular dynamics. And then I use Blender to make these figures. As from my hobbies, well, I like, as probably everyone, traveling, sport, reading. I like a lot doing outreach, scientific outreach in the schools. So here it was in a school in Barcelona like 3 years ago. And here at ICK, I'm also in the, let's say, worker committee. So you also like to remember that even though like we are doing science, we still have some rights. So it's good to keep our rights as well. So I'm done. And now,
Okay, so hi, I'm Enrique. Nice to meet you, all of you. I'm 24 years old. Sorry, I'm from Barcelona, but 2 years ago I moved to Tarragona to do my master on chemical engineering. So I've been in the UPC on Barcelona doing the degree on chemical engineering, and here at the URB doing the master. So my background is around chemical engineering. I have a background related with more kind of industrial work, so I'm not gonna enter with much detail on that because now I've decided to change a little bit my kind of work. I'm entering on the research field, and I entered last week in the Nuria group, and the next 4 years I will be doing the PhD there. Apart from that, I would take about background that I have been the secretary of the student chapter that we had in the university on the UPC in Barcelona. So there I had the opportunity to practice organizing events, practicing on explaining science to people. We had a lot of projects, like for example, we had our own brewing beer plant, which is something really interesting to explain and really funny. And then I think that I had the opportunity to develop some of my skills apart from the background that I had acquired, which could be that event organization, that teamwork, that developing my empathy and my responsibility sense on teamwork working. So I would like to see if I can apply those things that I have learned in some more soft project or soft dedications, and I would like to see if I can apply all those things in that new experience that would be getting a PhD.
okay, good. Thanks a lot, Enrique. So Mariam, this is you.
Hello, everybody. This is Mariam. I'm 26 years old and I'm from Iran. As my bachelor degree, I studied in Tabriz University in Iran as a ceramic engineering, working on nanoparticles and composites. Then I moved to Turkey to start with my master degree in Sabancı University as a material engineer again. Again, I worked on nanoparticles and electrodes, and I mainly work on energy field. Then right now I'm a new PhD student in NUIG in Solar to Chem project. And I will work on ligand stabilized metal mixed metal oxide nanocrystals for selective water oxidation. And I will use VASP for simulation of my mixed metal oxide to see their effects.
Thanks a lot, Maria. Then Santiago.
Hey everyone, I am Santiago Morandi. I am a chemical engineer. I joined ICIQ in October 2020, and then I start my PhD in the last paper. I am a chemical engineer, and I got my degree at Polytechnico di Milano University, where I got a specialization in process engineering. Until that period, my favorite areas were related to the field of industrial process automation and the design of chemical plants. That's the reason why I decided to do my master thesis in collaboration with VASP in Belgium, in which I had the opportunity to put into practice what I've learned during my master. I consider myself a curious person. I think that my curiosity and eagerness to learn led me to change, as Enric, completely my field, since I switched from the study of macroscopic scale of chemical plants to the atomistic scale of catalysis science. Then I consider myself also, I think I'm a collaborative person, since I think that in science, in order to innovate, the best way is through the synergy that we create with other people with different cultures and backgrounds. In my spare time, I like to play volleyball, since I've been a volleyball player for the team of my hometown in Italy for 10 years. I've been a middle blocker, and I spend most time playing volleyball than studying. I also like traveling, and I'm very interested in the modern history of the last 2 centuries.
Thanks a lot, Santiago. So, Ken, now you. No, there is nothing wrong. I mean, like, you were giving information about skills and other things, and you do this, like, like, there is no wrong. Go ahead and present what you did.
Okay, my name is Chen Liu. I come here and just doing the PhD in the Autonomous University of Madrid, and come in the 30-year student, and come here to the group of Nuria just to study some simulation skills to complete my work. And what I'm studying, just like the valorization of the chlorinate visit by hydrodechlorination with supported metallic catalysis. And the chlorinate compounds that I would like to study, just like the chloroform and the catalyst. That in principle, I use the metal palladium supported on carbon materials, just like activated carbon or carbon nanotubes, carbon nanofibers, etc. And the products, I mean, that we are interested in the hydrocarbon without the chlorine, just like the methane, ethylene, etc. And the scales that I used, I would like to do just because I'm just doing the experiments in the library. So the principal scale just use the equipment, just like some microreactivity reactor systems, and some in principle just like the gas chromatograph, and some software that I usually use just the Microsoft Office, R, Origin, Aston Pisces, just like this. And also, you mean when we have the catalyst used or reduced just like flash, I need to know the physics and the chemistry property about them. So in this list, in the right part, here are the principal characterizations that I know how to explain and simulate them, just like the TPD and TPR, and transmission electron microscope, just the time, and XRD, this thing just to know the property of the catalyst yield. So that's all.
Okay, so thanks a lot. Okay. Good. So that was mainly just to, let's say, to see where we are and also who we are, because it is a very important like part of the study. Then today class. So is like many of you, probably some of you already download this part. They don't put it like in the full screen yet. Sí, está reservada para 2 horas. Yeah, sorry. So like maybe some of you already download like this VASP like introduction. These are very nice and very detailed, but I will not cover them today. I mean, I will cover them, but in my own way. So I will mainly just go through the DFT section of my thesis, because I think that there you get all the information that you need. In VASP, on these other 3 documents, you get a lot of information that is really useful, but it may not be useful to all of you, because it's really, really hardcore. So I don't think that all of you will need that kind of level of theory, okay? But still have a look on the 3 document. This file will be online, but we will go through that today. And then this one here is basically like the hands-on section. So you have like a list of the exercise you need to do and some of the explanation, but we will also go through that today. Okay, so now I switch to my thesis. You see that unfortunately there is no presentation, because I wanted to go just like, since you will get this document, like I think it was smarter just to go straight to this document. Okay, so we just scroll down, and of course I will talk to that, and there are a lot of equations that are the most important things. Okay, so we start from the very basic things. The most important thing that you should all know when you do DFT modeling is that it's a model. So every model has a certain range of validity. That means that it's not that a model is right or is wrong. Like every model has limitations, and it's just that your model should be good enough to explain what you want to study. Because if you want to get a too accurate model, then it will take ages to do the simulation. But if instead you have a very simplistic model, then it will not work. So for instance, here you see like the second principle of dynamics from Newton. This works perfectly in everyday life. But if we study to use this formula to do DFT, it will fail miserably, because that fails under atomic scale. So that is important that we all remember, like every model has a validity range. You need to be very aware what are the limitations of your model. Also when you do your DFT simulation, because if you forget that and you just like take for granted that a model should be right, because it's a model, because it's theory, then you are, let's say, out of the scope. So what happened? As we say, like this model is not working in atomic scale, and since there were a lot of experimental studies from Einstein, well, Einstein was doing theory in general, but let's say there were a lot of experimental studies on X-ray by von Laue, Compton, etc. Then like Schrödinger, that you may all know because I was a kind of peculiar guy, decided that perhaps the way to solve this problem was to introduce a new formalism in physics, and this formalism was to kind of explain a physical system through wave function that you can see here. So from that, he wrote this very difficult equation that you actually don't need to know because you will not like go through that, but you know it's always cute to have that. So like this is the Hamiltonian of a system, and basically like you have equation based on this wave function. And what is important for you to know is that the way to solve a physical system is that you need to solve this equation. Okay, so this is an equation based on wave function. It's very complex, but the way to solve it is that you need to get this eigenvalue. So you need to get some real numbers. That means you need to get some numbers out of that are this EL. Okay, but again, like don't focus too much. It's just to show you that it's a complex story. And of course we cannot do that. But why we cannot do that? Because these things, so these wave functions, apply for every electrons. So what is the problem? Like the first approximation that you do in order to try to apply this equation on your physical system, so for instance on a molecule or like on a crystalline material, is to apply this Born-Oppenheimer approximation. So the Born-Oppenheimer approximation starts from, let's say, the hypothesis that since like usually like the nuclei are much heavier than electrons, then you can kind of decouple the two contributions. So you can assume that you have a nucleus, let's say in your atom, that has a certain contribution, and then you have the electrons going around that has a different one. So that means that you can start and move from this Hamiltonian, that is a complex one, to something that is a bit more clear, in the sense that you go to this equation, and this equation is the same as before, but it's just that now the Hamiltonian is given with three main factors. Here you have like K, that is the kinetic energy, that is kind of in a similar like formula that probably you already seen at school, like the standard law, like 1/2, the mass, in this case is the mass of the electrons, and the speed, okay? And then you have this other parameter that is the potential V, that is the potential generated by the fixed nuclei in case of many atoms or nucleus. So let's say you have just a nucleus in the middle that is generating a potential, and this potential is interacting with the electrons. And then you have the last parameter that is the U, that will be important later, that is the interaction between the electrons, because let's say in a system, in a molecule, you have many electrons. So just to let's say, to summarize this part. So like what the Born-Oppenheimer approximation does is just say, okay, look, let's decouple contribution from nucleus and contribution from electrons. And then he said, okay, look, we have the kinetic energy of our electrons, first term, this one. Then we have the interaction between the electrons and the potential that is given by the nucleus. And then we have the last term that is the interaction between the different electrons, because we have more than one electron in a standard physical system. And that's the reason, for instance, why Schrödinger equation can be solved analytically only for hydrogen, because there we have like one electron. You don't have many, well, two electrons, but well, actually you can solve it just in case of that you have one electron. So you have to have like a positive hydrogen, let's say a proton, that can be solved just for a proton. So what is the problem of this equation, and why we need to have DFT? Why we will arrive to DFT later? Because this equation, you need to solve it for all the electrons, okay, of your system. But the electron has three, like, let's say, usually to define where an electron here is, you need to have like the three spatial coordinates. So that means that you need to solve this equation, and you have, in the case of a very, very stupid molecule like CO2, the one that I've been working on for all my PhD, you need to solve a 66-dimensional function. And I mean, analytically is impossible. You may do it numerically. So the approach is like, okay, now we have a better equation than the, let's say, the normal like time-independent Schrödinger one. Let's see how we can solve it. And the way that, let's say, DFT, or well, people that make, let's establish the formalism DFT continue, was to say, okay, now we have an all-electron wave function. Perhaps what we can do is to take this equation and to split it for every different electrons. So you see here that you go from a wave function of all the electrons. So in this wave function, in this like function, you have all the electrons inside. And then you instead you write this wave function as a multiplication of wave function for each given electrons, okay? So that is, of course, much better, because now you have a multiplication, so you can consider one and the other and the other and the other. But what is the problem? The problem here is that we have this U parameter that, as we said, is the interaction between electrons. So if we apply this trick, so we decouple the wave functions of all the electrons and we split it for all the different electrons, then the problem is that in order to understand the interaction between all these different electrons, we will need to get these parameters. But in order to get this parameter, we will need to solve this equation. But in order to solve this equation, we will need to decouple to the different electrons. So we will need to go back here. So the problem is that it's a cycle. You cannot do that because you need to get an information that you can get just by solving the equation, but you cannot solve the equation without that information, okay? So that is one of the problems that then like was solved with DFT. And the last important part that you should like focus on, the last important trick, let's say, is that actually is the formalism of wave function is not effective at all. I mean, I'm sure that like many of you, if you never heard the concept of wave function now, they're like, what is a wave function? I have no idea. But why you have? Because this is just a mathematical formalism. Like wave function does not really exist. I mean, it's just a tool that allows for to calculate the electronic density, or better say, the probability to have an electron in a certain place. Okay. So what is important here is not that much the wave function, but is the electronic density. And you can get the electronic density out from the wave function, applying some very, very difficult operator that you see here that they are not important to know. What is important, like as a take-home message, is that the Schrödinger equation works well with wave function, but instead what is important, because experimentally you see that, is the electronic density, because the electronic density is the physical observable. You know, like if you do XRD, you can see electronic density. In a system, you see electronic density. If you polarize a cathode, you are increasing the electronic density. So it's something that experimentally you can see. You don't see how a wave function change. And so here we come back to the point of before. Model is how you try to reproduce an experimental system, but then you need to make sure to decouple what is physical, so what is really there, or what you just put as a tool on top of that to understand your system. Okay, so now we come to the Hohenberg-Kohn theorems that are the basics of DFT. Okay, why they are the basic of DFT? Because as we say, like the problem is that, okay, now we have this equation, we have the problem of this interaction parameter that we cannot calculate. We are splitting it for every electrons, good. But still, like, we need to calculate somehow this value from the nucleus that maybe you can still calculate, but this one is not that easy. And then you need to calculate the kinetic energy. So how you do that? Here they come these two theorems that really change DFT. Because in the two theorems, and I think it's like the reason why I wrote them here is because I don't think it's really easy to express the same concept in a different way. So the two hypotheses under these theorems is like the external potential, so as I say, is the potential like of this nucleus, is a unique functional, so it's a unique function depends only on the electronic density. Okay, so this theorem, like, let's say, allow you to relate external potential, the potential, a parameter that you know how much is it, to the electronic density that, as we say, is unobservable. It's something that you know where it is. Okay, so if you're able to calculate the electronic density and you know what is this functional, then you can calculate the external potential. So that means that then you can solve the previous equation. Okay, but now the trick is like, okay, but what is this functional? So here you're telling me, yeah, there is a unique functional. So that is like telling, okay, this is a function of something else, but this function can be quadratic, can be linear, can be logarithm. So we need to define that function. And here we come with the theorem 2, because here we are not really defining the function, but we are saying that the electronic density that minimizes the energy of this functional corresponds to the electronic density of the ground state, resulting from the solution of the many body Schrödinger equation. So what this second theorem means that if you get to calculate somehow the electronic density that makes that the energy of the functional is at a minimum, is at a global minimum, then this electronic density is the electronic density of your system. And since you know the electronic density of your system is something like knowing the wave function, then for electronic density, you can calculate all the other properties you know. So that's why these two theorems are so important, because before we were missing some pieces. We were missing, let's say, the way to calculate this external potential, this U parameter that we will again see later. But now what this theorem tells us is like, look, the external potential can be calculated as a function of the electronic density. And if you get an electronic density that minimizes this function, then this is the electronic density of the ground state of your system. So that is the electronic density of the physical system, let's say. So why this like system is already so important? Because now we are focusing on the electronic density and not anymore on the wave function. So the electronic density in a system is 1, the wave function, you have it for all the electrons, so you have many. Electronic density is just like how many electrons you have in a certain position, let's say. So like you don't have any more n electrons, but you just have electronic density of these n electrons. So you're already reducing from 3n dimensions to 3 dimensions. And that is already a hell of a lot of reduction, okay? And then the second thing, as I already said, is very, 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 very important. Because it's telling you that whenever you calculate something that minimizes function, that this is the electronic density, okay? And here, by using this trick, then they were able to develop these Kohn-Sham equations that are the one that you calculate every time doing the FT. So, as we say, we already managed to decouple. So the first trick with the R3 products was to decouple like the n electron Schrödinger equation into n single electron equation. So we move from one big equation that have like n things inside, and that becomes like a multiplication, a product of n single electron equation. And then what we do, so here you see that we don't have any more like phi n, we have phi I because that is, you need to calculate it for every single electrons now, okay? And then this now, the kinetic energy will be the kinetic energy of the single electrons. And this Vn now is the potential that is resulting from the electronic interaction with these electrons and atomic nuclei, okay? So by applying what we said, and these things will come up a bit later, these two theorems, but by applying this splitting of wave function of n electrons to different wave function, what we get here is that we can solve this equation. We will have n equations for every different electrons we have in the system, okay? So this is pretty good because we can calculate it kind of easily, in the sense that this is a kinetic, is a kinetic energy. So it's something that we calculate if we know more or less like the speed of the electron. This one, now it's easier to calculate because we told you before that the way to calculate this external potential, you know that this external potential is a unique function of electronic density. And that the electronic density that minimizes this functional is the one, is the electronic density. So it's like the parameter that will go inside this wave function. So these things you can calculate. This is just the repulsion between the electrons. But why you have this repulsion? Why this factor is a bit problematic? Because what we are doing here, as I said before, is to split wave function that include all the electrons into n different wave functions. But when you do that, what you lose is that now in this factor, you are considering the repulsion between one single electrons and all the other electrons. But in this, all the other electrons is also included the previous one. So the problem here, the problem of this factor, and that's why these things and these things need to be corrected. And this came why DFT is not correct, it's not analytical, it's not like a theory that is beautiful. Because you need to make further assumption or approximation to make it, let's say, to make it possible that you can solve it, okay? So this parameter needs some attention and needs some trick. And then the other problems came also from this parameter, this exchange parameter. So this exchange parameter, let's say, is just a parameter that you add there to account for everything that is not perfect. So as I said, this repulsion that shouldn't be there, the fact that you are assuming that all the electrons are different instead, like at the end the electrons influence each other, and all this kind of thing. So the way that you calculate this value depends on different methods. And so like all this, depending on the accuracy or the method that you apply, then you have different accuracy of your DFT. So we came back to what I said before. There is not like a perfect DFT or a bad DFT. There is just a suitable DFT for your system, okay? So now we have a way to calculate that, because we can calculate the electronic density. And the only problem, as I said, will be to find ways to have an estimation of these two parameters, okay? And just to summarize what is the cycle, so whenever you submit a DFT calculation, what you do is that, so your system, let's say your VASP like software start, VASP see that you have a CO2 molecules, and he said, okay, CO2 molecules, I have a carbon, I have two oxygen, and he start with a guess of the electronic density. So he define, okay, the electronic density in this position should be this, in the other position should be that, in the other position should be that. Then he used this electronic density to solve these equations for all the electrons that you have in the system, okay? And then by solving these, and then for electronic density that you started with the gas, then you can calculate this, then as we say, you can estimate it somehow, then you can calculate that single electron wave function. So you can calculate this one because you know the electronic density, you solve the equation, you calculate the wave function. Then since you calculate the wave function, from the wave function, as we said before, you can calculate again electronic density. So let's say you start with a gas, you solve equations, you get an improved gas, and then when do you stop? You stop when you see that the updated value of the electronic density and the old one are within a certain threshold. And that is probably the most important thing still now, or at least the only thing that you should remember. Because all the other things is basic, strong, hardcore, DFT that you will never need to use. But what is important is for you to understand, then again, you will never converge a system completely. You just set a threshold where you say, look, I think that the electronic density in this system is converged well enough. So I can take some physical understanding out of it. But you will never say, look, this system is exactly the same as the experimental one. Because it's simply not, because as we saw, we did so many assumptions and hypotheses and approximation that it cannot be. And so what happened? If instead this one is not, let's say, close enough to this one, so there is like, for instance, like this N1 is much different, so that the overall energy is much different, then we start again the cycle. Then this will become the new gas. So you start with that, then you solve again, this N0 will become N1, then you solve these Kohn-Sham equations, then you determine the single electron wave function, from that you get a N2, so updated electronic density, and again you repeat the same, until you go to see that this N2 minus N1 is within a certain threshold that is good for you, okay? So this was like the main important things. Now, just for kind of like giving you some ideas about other things that you will see when you do DFT, is like you will see that you need to use different like functionals. So what does it mean, the functional? We say before that what these two like theorem that we saw before say is that you can define a unique functional of the electronic density that can give you the external potential. So the way now is to define this functional, okay? So you need to find a formalism to calculate this functional. And as we say, like there are these two parameter exchange correlation that are basically like coming from the fact that you are assuming that all the electrons are split and there is no interaction between them, but it's not correct. And then you have the fact that you are assuming repulsion between an electrons and also the same electron taking as in the group of all the other. So there are a lot of assumptions, a lot of approximations that are not that correct. So in order to fix that, you need to define this very last parameter. So these things, the only one that you cannot calculate, okay, that you cannot get more or less like, let's say, analytically. So how do you do that? There are different approximations. I will point out the one that we are using, but we start historically, okay? So the first one is the local density approximation, LDA. We will never use that. This is a tag that you will see in your income file. So this is like a parameter that you will set inside your file to say, look, I want to use this functional on the other functional. So what is important to remember here? This is the approximation 0, okay? So the way that you calculate this parameter, so this exchange energy, is simply assuming that the electronic density in the in a certain position is the same as an homogeneous electron gas. Okay, so you can see that, I mean, this is a very, very like harsh approximation, because an homogeneous electron gas, I mean, may work for some gases, may work, for instance, for some of the systems, like for a bulk solid, when you have all the electrons that are shared, but in our case may not work. So that's why we never use this, or at least in our group. Well, we never use this anymore, because I mean, that was good at the beginning, but now becomes much better, you know. For instance, you can see that you can overestimate bond energies by at least 2 electron volts. That is a lot. The one instead that, well, an improvement comes from the GGA, so generalized gradient approximation. So what do you include here to improve? You simply, instead of assuming that everything is an average, so the electronic density is the same as this homogeneous electron gas, what you do is that you also consider the gradient of this electronic density. So that means that what you do with this GGA is that you don't say anymore that you can get this exchange factor just by integrating over like the electronic density and like this factor that is like the electronic density for a homogeneous gas. But now you take a product of electronic density and its gradient. So you are able to see also local variation of the electronic density. And so that's the reason why, for instance, like in our group, we use this PBE, the Purdue-Burke-Eldernoff functional, because this one is better because you have the variation that usually in a catalytic system, for instance, you have. Okay. What is the problem with GGA? The problem with GGA is that it doesn't account for these London dispersion forces. So you will see in the following on the answer that sometimes, like in DFT, PBE, for instance, we introduce the DF2 like formalism that simply means that we need to include van der Waals correction. So if you calculate absorption energies, where, for instance, like van der Waals can be very important, maybe because you have explicit solvent molecules, so you have water around, all these kind of things, then you need to include other correction, because van der Waals alone will not be, well, PB alone will not be enough because it doesn't include dispersion factor by themselves, okay? And then you can increase the accuracy, because you can go to the second order derivatives, and you go to meta GGA functional, and the very, very last ladder of the stairs. So here, like in DFT, like they used to express it like that. Okay, so you start with the simplest approximate LDA, where you just assume electron density. So GGA, where we have PBE, the one that we use, where you have also, you are also accounting for local variation of the electronic density as like first derivative, meta GGA, and then let's say the highest one, that means the most accurate one, is hyper GGA. Because here, what you have, you're also calculating this as exact exchange. So that means that you're also like considering carefully every atom you have, and you don't take anymore any approximation, but you'll go very, very close to what Schrödinger equation will tell you. What is the problem of this hybrid GGA functional? You use them sometimes when you calculate like very, very difficult oxide, or well, semiconductors, or system where you have a very, very harsh localization of electronic density somewhere, but they also take a lot of time. So to make you like an example, a take-home example, like if you calculate the band gap of a semiconductor with PBE, that may take like, I don't know, let's say 30 minutes maximum. If you do the same calculation with the hybrid GGA, that can take 28 days. So you see, like, of course, you get a much better band gap, but it's also taking like much more time. Okay.
And I have a question.
Yeah.
The PBE GGA just like a meta GGA.
The PBE,
Yeah.
it's no, it's I mean, the one that we use, no, it's just a GGA as far as I know. So it's in this line because we are just taking for one gradient of the electronic density. Okay. And then we are really close to the end of this section. That is really, that I know that is really heavy. But don't worry, the next lectures will be much more calm. So now I will say we are close to the end. Why we are close to the end? We are close to the end because you see here, like, let's say, like, so all these things worked for molecules or atoms, but we are lucky because usually in catalysis we work with periodic systems. So for instance, if you take like a metal is a periodic system. A bulk crystal is a periodic system. And so you can apply further trick, okay? So I suggest you to have a look on the Kittel book. I mean, probably some of you already did for the master or bachelor. But what is really important, mainly because in DFT we use that, at least in a heterogeneous catalysis, well, the one that we do in the group of Nuria, is that whenever you will get a structure, the structure that you will get, that you need to calculate with DFT, with VASP, let's say, better say, will have like the primitive translation vector. So you will see like the structure that give you like a periodic cell, because all the systems that we are calculating in the group are periodic. So it means that you need to find the like primitive cell. The primitive cell means a cell that can be repeated in the 3 dimensions, so X, Y, Z, okay? And usually you define it like this, that there should be like, let's say that every new atom in this cell, like the position in every new atom should be given by basically like a sum of the different lattice vectors multiplied by a certain like integer number in front, okay? So that is important because that is like whenever you do, like you see a postcard that is like the structural like file for VASP, then you usually start with atoms that you have, and then the 3 lattice vectors, so A1, A2, A3, that usually have also X, Y, Z components, and then you have, let's say, like other factors. But the fact that a periodic system is defined by these 3 main vectors, A1, A2, A3, that define the primitive cell, or the Wigner size cell, as you want to call it. And then we go to another like formalism, because this is something that you can see, because this is something that you see directly, and then you go to the brevet lattice, and then instead it's just the reciprocal lattice. And so you can calculate it from the lattice vector, as you see here. But what is important of this, and also the fact that like the reciprocal lattice relative to the primitive cell is named Brillouin zone, is just that this Brillouin zone, this reciprocal lattice, is the space where the key point sampling will happen. And like in a second, I will tell you what these key points are, okay? So the key points we will see later, but these are important parameters for DFT, for VASP calculation, okay? So you need to remember, like, there is a physical space where you have like periodicity, and then by taking the reciprocal of these vectors, you have the Brillouin zone, or the reciprocal space where you can locate the Brillouin zone, that is the reciprocal of the primitive cell, okay? And this Brillouin, or well, this reciprocal space is the space where the key points are, or where like all these key points are important. And you will see now what these key points are. Well, you already know, probably many of you already know that the way that usually, like this notation is good for bulk system. Usually if you have surfaces, it changes a bit. So the way that you define surfaces through its Miller indices. And the way that you calculate the Miller indices is just to, let's say you define a surface orientation just by the reciprocals of the intercept of like this surface with the 3 like axes, okay? So that means for, and usually like if the plane does not intercept an axis, then the corresponding index is 0. So for instance, a surface that is defined by 1, 0, 0, that means that is a surface that is parallel to the y and z axis, because it doesn't like meet the x and y axis, and instead like as an intercept on the x axis at the point 1, okay? Okay, and then we go to the very last hard concept of today, that is the Bloch's theorem. And the Bloch's theorem is what enables us to calculate, like, not to calculate, but like to simplify a lot of the things that we do in heterogeneous catalysis, okay? Because there are 2 ways that you can account for the atomic orbital, let's say, there is like, usually in homogeneous catalysis, like you use much more like basis set, but instead like, you know, heterogeneous, that is the important one for us, we use plain waves basis set. So that means that we can use the periodicity of the cell, because every surface will be periodic, every bulk will be periodic, to simplify our system. So what is the key take-home message of this block theorem? It's simply that since you have a crystalline surface, a crystalline structures, then also the potential energy of the electron will be periodic, okay? So whenever you have a translation R, that is the one that we saw before, this vector that is given by a combination of different like the three lattice vectors, then also the potential energy of the electron is periodic by the same extent, okay? So that means that you can define, let's say, the single electron wave function of your crystalline materials will also have a periodic part. And this periodic, and you see it here. So let's say the important part is that the potential energy of the electrons is periodic. That means that if you find that if you apply a translation, then means that the potential energy of the electron will be the same. So that means that your like wave function of a single electrons will also have a periodic part. Okay, this one, the periodic part, and this periodic part will depend on wave vectors k. I know that this is really complex and is really like hard, but focus on the important part. The important part is that in the ACAR file, you will see a parameter that is called kinetic energy cutoff. The kinetic energy cutoff is basically telling you where you want to stop this sum here, okay? So that means that if you take higher energy cutoff, then this U, so let's say this periodic part of the wave function will be much more accurate, but will also be much more time consuming to calculate. If instead, if you take very, very low energy cutoff, then this value will be very bad. So also the wave function of your system will be very, very badly calculated, and so you will not have meaningful results. So what is important here for you to get from this block theorem is that you can assume that also the potential energy of the electrons are periodic, and the way that you can account for that in calculating the wave function is simply by calculating this periodic part as a function of the kinetic energy of the electron, let's say summing all the kinetic energy of the electron that you have in the system, or of the states of the electron that can assume in the system, better say. And so that means that if you calculate a lot of possibilities for these kinetic energies, then you have a much more accurate result, but it is also taking much more time, okay? And the other important parameter, you see here that this wave function is calculated by this factor that we already defined, is the one with the kinetic, with the kinetic energy cutoff. And then here you have an exponential, and this exponential has this k. This k is defined as the key points. That is the one that I told before when we were talking about the reciprocal space. And again, like why key points are important, because you will see also, well, tomorrow when you do the hands-on, that you have a file in VASP that is called key points. And inside you are defining the number of key points that are assuming. Take home message, what are these key points? These key points is more or less like the grid that you have in your electronic discretization of your system. So let's say it better. If you have like a surface, and on a surface you just take a single key point, that would be like if on that surface you just assume that there is like a continuous average electronic density. If you take instead much more key points, like let's say you take 4 key points, it's like if you are dividing this surface in 4, and you say, okay, here there can be a value of electronic density, here can be another value, here can be another value, here can be another value. So more key points you apply, more discretization you have, more meaningful your result is. But as with every software of engineering, more discretization you have, longer the simulation time. So again, as with the kinetic energy cutoff, also here you need to find a compromise. So you need to select the key points that are good enough so that your system makes sense, but not too many key points, because otherwise your system will take hours and hours and hours and hours to converge. And here we are very close to the end. Now we go to the answer.
Federico,
So, yeah.
excuse me, I couldn't understand the key points, to be honest. Would you please repeat it one more time?
The concept. Okay.
The key points, yeah. Please.
Yeah. So the key point, like, they come from this block theory, let's say the formalism. And the way that is defined, it's, yeah, like, let's say, like, because here is, I think it's defined better than what I say. So the single electron wave function, so these things, is defined by product of this periodic, like factors, that is the periodicity that you have in your system, plus this exponential, and this k that you see here, these are the key points, okay? So that means that you calculate the agent state, or let's say you solve, let's make it very easy. Maybe it can be a very harsh approximation, but I think it makes sense to understand it better. It's like if you were solving this wave function for each key point. So that means that if you just have a single key point, you are assuming that you have the same electronic density in all your system, okay? If you have 4 key points, you are instead saying, okay, for each of the key points, I can have a different electronic density. If you have 100 key points, then you have a different electronic density for all these 100 key points. So, of course, like, the number of key points depends on the accuracy that you want, but also on the size of your system. Because if you have a cell that is like 10 angstrom per size, then yeah, maybe 3 key points are okay. If you go with a cell that instead has 100 angstrom, you should also scale your key points accordingly. Because otherwise what will happen is that you will have like a lot of discretization there, or not as much, okay? So that is the important point, like that you need to see these key points, or this key points grid, as the degree of discretization that you have in the possibility that you have in calculating the electronic density. Like, to every key points, you can kind of associate a value of electronic density. Like, in every key points region, let's say, in every key points like portion of this region zone, you can associate the electronic density. So more key points you have, more discretization of electronic density you have. Less key points, worse discretization, and so for some system will fail. And that's the reason why usually you need more key points when you have a semiconductor. With a metal, enough, but not too much, because in a metal you can assume that like the electronic density is well shared, so you would not expect that many variation between the different like atoms, let's say. But for instance, like, and even less in a molecule, because in a molecule, in a small molecule, the dimensions are small, and it's okay just to calculate the overall electronic density. You don't have that much variation. Okay, is it better now?
Yeah, thank you.
Thanks to you. Okay, then we go to the very last concept of today, and it's also the last concept that you will see. Like, in the hands-on that you will do tomorrow, you will have this pod card. What is the pod card? The pod card is the list of the pseudo potentials. The pseudo potentials are done by the VASP, well, the people that did VASP. So you don't need to think about that. What is important just to know is that all the treatment, all the things, all the discussion that we have until now is based on the concept that we need to solve this Schrödinger equation, taking up wave function for each of the electrons. And I mean, even if we did a lot of approximation, we can decouple the different electrons, a lot of things. I mean, it's very clear to see that more electrons you have, more complex the system is. And I mean, in chemistry, it's also important to notice that usually, like, the electrons in the inner shells are not that important in the overall performance of your system. What is very important are the valence electrons, because usually are the valence electrons that reduce the reactivity, while the inner one, yeah, I mean, you see some difference, but not much, okay? And that's the reason why there is a periodic table, because if, you know, so if the inner electron were so important, then probably there will not be all this strength between group and series in the electronic table, in the periodic table. So what is the pseudo-potential approximation? The pseudo-potential approximation, you can see it very clearly here. What the pseudo-potential approximation is just assuming that after a certain radius of the atom, let's say so, like for the electrons in the inner levels, like instead of applying all these wave function, what you can do is just you can take these inner electrons as something that generate a pseudo potential. So that means that like beyond this radius, you calculate properly the wave function, you assume each of the electrons, all this kind of thing. If instead you go to like electrons in the inner shells, then you don't need to apply the Cohn-Sham equations and so like the Schrödinger equation, but you can just say, look, all the contribution of the electrons in the inner shell account for a certain value that I can tabulate because I know, and so it's done. So what is important of the pseudo potential is that allow you to do calculation much faster, because then you, if you have, for instance, let's take copper. In my case, copper, I was just assuming 11 electrons, the ones that are in the valence. I was not assuming all the electrons of copper, because the ones that are in the inner shells are not that important in their activity. And there are also different class of pseudo potential. Usually we use PAW power. Okay. So that is, and well, the last thing to say is this one, that usually like there are two properties for the pseudo potential that for sure, I mean, they're also rather like easy to get. They are either transferable or soft. What does it mean? If a pseudo potential is soft, so it means that you kind of, let's say that you are assuming that a lot of things happening in the inner part are not, wait a second. Oh yeah, so the soft pseudo potential, you are increasing the accuracy. So what it means is that you can just calculate like your system with a very low energy cutoff, because you, let's say you have a very good definition of your inner properties. And instead, like in the transferable pseudo potentials, what you have, like the other quality of being transferable means instead that it's kind of the opposite of being soft, is that these pseudo potentials are good enough so that you can calculate the inner electron properties irrespectively from the atomic valence electron. So let's say there is much more relevance on the on the inner electron. But I mean, these two concepts here, don't focus much on that, because I mean, I put in the thesis, but it's not something that you will have to think about it, because usually there are standard pseudo potential for your system, and you just change the pseudo potential if you see that your system or your simulation is not working well. Okay, but it's not something that you need to think every day. Okay, then I think that for today this theory it's enough. So what I propose before we go through the answer, if you don't have question, we can have like 5 minutes break. So you can like go to the toilet, rest 5 minutes, and then like at 11:15 we come back here. Yeah.
Just for standard system for the for example, the plugin and with normally a book one with just 111 space. The standard words value for key points normally is.
I mean, we will go through that. We will go through that. Like that will be the true lesson. But usually, what you need to do, okay, and then we come back to probably what is important. That is this. Is that usually whenever you have a DFT paper, you have computational details at the end. So in all my paper, in our paper on the group with DFT, you will see almost the same things. And this is basically what we say till now. So that we use VASP, then we use PBE, then we use inner electrons, we calculate them explicitly. Well, inner electrons, we simulate with pseudo potential, this PAW pseudo potential. We have a certain kinetic energy cutoff, that if you remember is the one that we needed to put through the, thanks to the block like theorem. And then here we go to the key points. Brillouin zone with a gamma center. This is just like a specific like position and key point. And then large enough to provide a reciprocal grid size smaller than 0.03 angstrom to the power of -1. So what does it mean? This number means that like to define what you just asked, Sichen, it depends on the extension, but let's say if you take the palladium 111, for instance, what you need to have is that, well, let's say the rule of thumb that you have is that you multiply the vector per the number of key points, and this number needs to be 30. So for copper, for instance, like if you take copper 111 and the lateral dimension are like 3 per 3 angstrom, then it means that you need to have a key point sampling of 10 per 10. So x 10, y 10, because 10 per 3 gives 30. Okay?
Okay, not okay.
Okay. So like just to make it clear, maybe I can. Okay, let's see. I always forget this one should be. Yeah, so you have a periodic cell, okay, the one that we just said. So we have these things. If this is 3 angstrom and this is 3 angstrom lateral size, here we are talking about a cell, okay, like a surface. So usually a surface we say that is periodic. So that means that you will have here the layer of the surface, 4, 5, 6 layers, depending on how many you have, and here you have vacuum. We will see all these like carefully in 2 lessons, okay? So don't worry too much about that. But what is important is that this multiplied by the key points mesh that you put, so in this case 10, needs to give 30.
Okay.
And the discretization is just important in the x and y axis, because on the z, since you have vacuum, is not that relevant. So usually, let's say in this system, the mesh, the key point mesh that I would put, so kx multiplied by ky multiplied by k, okay, really bad in writing with zoom, will be like 10
30
per 10. No, this is the key point mesh, and 3 per 10 needs to give 30. Okay, so it needs to be 10 per 10 per 1, because this is the one that you put on the z, and on surfaces on z you always put 1, because you are not, it's not that important for you because there is the vacuum. I mean, you don't care much to have a lot of discretization on the vacuum, because in the vacuum there shouldn't be electron density. Okay. So this is the take home message. So I think we can do it now if you want. 5 minutes break, so we all rest. Then at 11:20 we see each other here again, and we go directly to the answer. Okay. Good. 10 angstrom usually. The vacuum should be around 10-12 angstrom.
Pero después calcular que después no va a caer, no va a caer, porque no va a ser disminuir más pequeño.
It depends on the system you have, but should be around. I mean, it really depends, but usually like the vacuum, you always assume it at least 10 to 12 thickness, okay? Because more vacuum you have, longer the simulation. Okay? Okay, so now we can come back.
No sabía que jugabas muchos amigos que juegan aquí.
¿Tienes amigos aquí?
Sí, que juegan en equipo. He ido a ver algunas veces y no, es un deporte que yo no.
¿En el equipo de Catalonia?
No, en Barcelona, pero uno ahora vendrá aquí, pero a Reus. Juegan Reus. Pero sí, sí. O sea, antes eran 3 que jugaban juntos, unos niños.
¿A qué hora está pensando de probar aquí en el equipo?
si quieres hablar con mi amigo, creo que
No,
es...
eso también Federico creo que habla.
Ah, sí,
¿En serio?
pero sí, en Reus. Sí, porque ahora me perdí la conversación.
No, le estaba diciendo que tengo muchos amigos que juegan a voleibol.
En Reus, ¿no?
Uno
Oh.
de ellos ha venido ahora a Reus,
Ah,
porque son de Barcelona, pero
Vale.
justo se ha mudado.
¿cómo se llama tu amigo?
Xavi
no,
Herrerías.
no.
Es que ha sido...
Pues no, porque al beach volley llegó una otra persona que jugaba, que era de Barcelona y que creo que vive en Reus, pero no se llama Xavi, se llama diferentemente.
No, pero él vive en Tarragona. Lo que pasa es que
Vale.
juega en Reus porque dijo que creo hablo de voleibol de pista.
Sí, porque hay
Claro.
primera catalana, creo que hay primera catalana también en Reus y de hecho aquí en San Pere también. hay
Correcto.
primera
Creo
catalana.
que él probó en San Pere, pero le gustó más Reus.
Sí,
y por
sí.
eso va a Reus.
Es que Reus es más como en San Pere, en primera catalana, es un grupillo de gente joven y en Reus un poco más gente ya que trabaja y lo hace para disfrutar, ¿sabes?
Ya.
Es diferente la mentalidad y todo. También porque en San Pere tienen la Superliga 2 también, ¿sabes? Entonces, claro, en San Pere la primera catalana es el segundo equipo y en Reus, en cambio, es el primer equipo. Entonces,
Yo un deporte que nunca había jugado ni nada, pero viendo a mis amigos jugar, se le he dicho, ay, pues está muy guay.
Sí, no, está
Es súper
bien.
emocionante.
Está súper bien, la verdad. ¿Qué habla? Voleibol.
De voleibol, del deporte. No sé si ya se os ve un poco altos a vosotros ya. Yo no tanto, es más.
Yo por eso jugaba de libro.
Amigo, ya.
No podía hacer mucho.
¿Cuánto mides tú, Santiago?
Soy como 1,96.
Okay, so here we are. So before moving to the last presentation, I just stop and share again because I want to make sure that I'm sharing all the screen now. Just because, everything that I say today will be much better explained if you're curious on the books. So here I put 4 books that I think they are really relevant, at least they were really relevant to me. So the Kittel, probably some of you already know. I mean, that is an introduction to solid state physics. And all these things that I say about the block theorem, key points, is for sure explained much better. So just have a look. The first 1 or 2 chapters are very properly explained. I studied it myself on that when I was in the physics master and was really good. So I suggest that. For DFT, this book as well. This is like a practical introduction. So this is saying more or less what I did, but of course with a formalism that is much more advanced than me because these people are working on that much longer, okay? And then the last things I put, if you are interested, maybe some of them already know about that. This is fundamental concept in heterogeneous catalysis. This is from Norskov. And this is rather nice because you have a list of all the things that you can calculate with DFT. So, you start with surface equilibrium, then you go to rate constant, the kinetics, energy trends, activity and selectivity map. So this we will not cover this aspect because here we are really entering in science, but can be interesting for you. I mean, I read it all when I started and it was really nice. And the very last things, but just in case, I mean, that really depends on if you work or not in electrochemistry, but I put it here because the book is simply beautiful. So this is the Bart book. So this book for electrochemistry is kind of the Bible, experimentally and theoretically. So if any of you at one point work with electrocatalytic system, I would really suggest you to have a look on some of these chapters. Mainly because usually in the DFT is based or work very well for thermal catalysis, but not that much for electrocatalysis. So it's good to have a proper understanding of electrocatalysis, because otherwise we can make some mess. Okay? So like all these useful books are in the share folder, so feel free to download them, check them. I mean, it's not that legal that I'm sharing them, but you know already, so it's okay. Good. So now we are ready to go very quickly on the answer. So, okay. So Mariam, you also see them, right?
Yes.
Okay, cool. So for the first class, you have like this 10 system to calculate. Okay. So just to go quickly over them. These are mainly molecules, as we say. So all of them are molecules. These two are vibrational frequencies. And this is ab initio molecular dynamics. Okay. So why is important? Like I wanted to make some kind of example, because otherwise, you get lost, like, but why we need to calculate these things now, I mean, it's not just to learn how to calculate things. It's actually that many of these things are important in general. So you need to know how to calculate molecules, because molecules are important as reference energies. Because in DFT, a lot of parameters are based on formation or absorption energy. That means, let's say, the way that you're binding an intermediate on the surface. And let's say, if, for instance, I want to calculate the binding energy of CO2 on this surface, then I also I also need to know how much is the energy of the CO2 alone. Because otherwise I can take the energy of this system minus the energy of this other system, but these two systems are not the same, because this system has a CO2 and here I don't have. So I also need to have a third calculation here that tell me how much is the energy of a single CO2 molecule. And the problem is that this energy needs to be properly calculated. So that's why here you have 1, 2, 3, 4. You have 4 different setups, because you will try with oxygen atom without spin. You realize that the energy is really bad. And then you will try to add spin. So add spin means to consider these oxygen atoms magnetic. Then here you are breaking the symmetry, because the problem is also that since it's a periodic system, it also depends how you put the atom. Because if you, for instance, you put the atom to symmetric, then maybe your VASP algorithm is not able to break the symmetry, and so you get a value of energy that is not the proper one. And you will see that the best calculation will be the oxygen diamond, because oxygen experimentally comes as a diamond. Like, of course, there are also oxygen like ions, but then you calculate CO, vibrational energy for CO and water. This is important for spectroscopy. This is important for spectroscopy because if you know the vibrational frequencies, that, for instance, you can reproduce like infrared spectroscopy, Raman spectroscopy, and it's not that used in DFT, but trust me, is really, really powerful. Because, I mean, at least to my personal understanding, like this is probably the one of the things that DFT can do better. Because like the algorithm is rather robust, and you can really get closer to the experimental system, because at the end, like the way that experimentally you do spectroscopy, I mean, you see how these molecules are absorbed on the surface. And in DFT, we do exactly the same, because we just absorb molecule on the surface and we see how they interact or how they vibrate. So like these are really important. Then the CO state is mainly about electronic state, you will see. And then this is ab initio molecular dynamics on water. So there is a water molecule alone. You apply ab initio molecular dynamics, and this is important to calculate dynamic processes. On the hands-on here, on this file, there are many things. So there is an explanation of each system, some details, and I would like you to check that and to do it alone. I mean, here I will just introduce you to how you need to run the system. So very, very related to our own computer. Tomorrow in this 15 minutes each, we can discuss more aspects, but I would really like you to try, because I mean, like, you should, well, not fight with it yourself, but like, at least like, you should be curious and experience the things yourself, because like, These systems are easy because you get everything done already, but then the real system that you will calculate will be more difficult because then you need to set up yourself the models. So it's very important that you get to know everything yourself. What instead I want to do now with you is just, I mean, we don't do that because I say like, you don't have your computer. Like I put all the important information here. You will get this PDF, so don't worry about that. It's just, I go quickly on the steps you need to do. And then after that, I will just open the virtual machine here and do it quickly here. So on this video, you will have all the things. So you will need to connect either through on the virtual machine, Mariam, or through AnyDesk, Santiago and Rick, you can. You open a terminal, you need to enter Tecla because what we want to do now is to submit simulation. To submit simulation, you need to enter the supercomputer interface. You cannot do it locally because you don't want to run this system on your own ICQ workstation. You want to run them on the supercomputer or that is Tecla. So you enter Tecla home, or better say you enter Tecla, you enter the supercomputer. In the case of Mariam, like you will need to enable this better juice tunnel to enter, but for all the other, this is enough. So SSH Tecla 2, I'm sure that all of you already did. Then in your home folder, you need to make a directory that you do with this command mkdir. Probably you already saw that in this list of commands for bash. And then inside this Anson, you also make another subdirectory that you call 1, because that is Anson 1. Important things, I already told Marian, some of you already know. Try to avoid capital letter and try to avoid space. I mean, space are perfect in Windows, but in Linux are terrible because then space like Linux doesn't read it. So every time make sure that you name things short, clear, and all lowercase. Why you don't want capital letter? Because otherwise, if you will not be fast anymore typing, because then every time you need to go, okay, this is capital, this is not capital. So just go straight to the point. Answer /1, clear. You will have the exercise of answer 1, just the first one, because I don't want you to get to that first, on my Tecla home. This is a very powerful tool that is important for you to know. Like all our Tecla home folders are connected. So you can always check what a colleague is doing. You can always take like data from other colleagues, not steal data, like copy data. So you cannot remove other data, so don't worry about that. But you can always like say, okay, like look, you have a file that I don't have, I copied from you. Okay, so I have it there. You will copy that in your folder. And then you need to check with this ls-lt that you successfully copied that. And then here it goes to the big part. You have the PDF of answer 1, where there are all the instructions. You will need to go one by one to check the in card, the key points, the postcard. Like later, very quickly, we will go through them just for you to see. But these are the 3 main parameters. So in the in card, you have like more or less the definition of what you want, what calculation you want to do. So ab initio molecular dynamics, there will be some parameters, optimization and other parameters, duration of frequency, other parameters. The key points is the key point sampling. So the one that we saw before, like simply like how many key points you have, how they are positioned and all these kind of things. And then the postcard is instead just like the crystal structure. So these are the position of your system, okay? So you will need to enter, you can check them. I suggest you to use the VI editor. So VI is a powerful tool because on the terminal, I mean, all these things you need to do them on the terminal, okay? So you just need to type things on the terminal and you can simply see the incar and then check. You open the VASP manual, you check all the different tags. If you don't understand something, you may ask tomorrow, but check, because it's important that you understand properly what you're doing. You know, like you can also just run all the simulation like in 1 second. And then in 3 days, you have the result. Well, you have the result in 1 minute actually, but then in 3 days, you have everything. But you don't understand anything of what you did. What is important now is to understand, because these systems are very easy. You will not work on this system, but this system is just made because you need to understand, okay, now I'm calculating this because I want to go there, because I want to do this, okay? You check also the structures, and in order to check the structure, you need to do it locally. So that means that you don't do it like on Tecla, but you do it on your own workstation. So for the one that use AnyDesk, that is simple, you don't need to do anything, you just need to do CD Tecla home. You need to enter the Tecla home folder that is already mounted on your own computer. In the case of Marian, you will need to like use these 2 commands, like tunnel 1, tunnel 2 with your username. okay, into different terminal. And then we will see later that is a kind of powerful tool, the Python for VASP tool, that is a tool that allows you to visualize the system that you have and also allow you to see like the energy of your system and many other things, okay? And the last things, that is the important one, is to submit simulations. So we submit simulation again on the supercomputer. So on Tekla, like this is again, this is not local, this is not ICQ workstation, but you will need to be in this SSH space Tekla 2.icq.es because you need to be in the supercomputer. I have myself a file to generate run file, so you can copy it from my bin folder. I mean, well, more than you can, you should, because then it's the same. You will see that you can also go to this run file. I mean, this run file is just a file that creates this run.sh file that is the one that you need to submit a calculation. And this run.sh is something that we have ourselves for Tekla. It's not the general one for VASP. We just have it because in our computer is working like that. What this run.sh file does, usually it notifies you whenever you submit a calculation or whenever like this calculation die or all these kind of things. So you need to go to this run file and change every time you see Dattila, because otherwise, like every time you submit a simulation, I mean, I will get an email myself, okay? And there is no problem. I mean, I love to get spam, but still, like at one point you need to change it. In your case, Mariam, like you will keep the same because you don't have ICQ email, but it doesn't matter. But for the others, since you will stay here longer, please change. And then like this, executing this command, you will create this run.sh file. So rungen space name of the simulation, and you can call it as you want, like test, ciao, mami, whatever you want. I mean, usually I suggest you to give meaningful name, like sim1 atom, something, oxygen atom, like this. 4. The first 4 is the queue. So we will submit to the C4. And the second 4 is for the number of processors that you will use. Very, very low, because these are just tests. These are very, very easy simulation. And this is the VASP version that we will use. 5.3.5. In the future, you will use 5.4.4. But since these are very, very stupid systems, it's okay. You need to change the executable. So in order to change the executable, there is a powerful command that is set. So by applying these on the run.sh, what you are doing is you are changing every time you have a VASP _std to a single VASP. Okay, so you need to execute this command, and then to submit on the supercomputer folder is just you enter that folder, and since you will have already the run.sh, you just do q sub space run.ch, and that means that you are running a simulation. Okay, since you have 10 different simulations, you may consider doing a 4 cycle. Okay, check all the cycle online because they can be very useful, because in this case, then you can do this and this for all your system. You don't need to enter each of the folder yourself manually, and you save time. And the very last things, you check the result. So on the Anson file, you will get some instruction. They will tell you, look, check the magnetic spin of this 110 atom. And so like you can check things either with this Python for VASP editor, vasp.xml, or opening the outcar file. This is the other output. So that was the very, very big picture. You see, like we went very fast through that because this is mainly for you to have them tomorrow and today and to check them when you're doing not now you don't need to learn this by heart because it's not the time to do that. So now what we will do is we will close this presentation and I will open the virtual machine. So we will just go very quickly through them, and I will show you what it means to enter Tekla, where you find the file and all this kind of thing. Are there any questions?
Not for now.
Good. Okay, now we are coming.
And we should learn all of the properties for Incar.
I mean, again, like, yes, you should have an idea about the factor. Now I will show you what I mean for having an idea. It's like you see a inker and you should have an idea of why this. Okay.
Got it.
Oh, yes.
Yes.
Okay, yeah. Just that the other microphone, but it's okay because I will use my own one. So.
There's a problem again. Yeah.
No, I think it's something.
Yeah.
Oh,
It's like,
okay.
I can hear right now.
Okay, well, let's hope. Okay, I hope. Well, just I can still hear you. So if at any time you don't hear, just talk and tell me, oh, I don't hear, because then we stop directly. Because now I try with any desk. Okay, so like that is not anymore virtual machine, but it doesn't matter. So now this is mainly for Santiago and well, Fiken and Enrique. So as I said, like in your case, it's much easier because you just enter like tecla home VASP course, Anson 1. There are the bunch of simulation you need to consider. Here there are the 5. So INCAR. You see that like in this case, it's really easy. Okay, now you listen to me, right?
Yes, I can hear.
Okay, so there is basically a system that is not important and is near. So what is important here is just that you copy this is near, you put it on Google, and you check, okay, what does it mean Gaussian near? Also in the Anson slide, there is a description, but that's what I mean if like when I talk about checking all the input, okay? Then like you have the postcard. The postcard is just like, okay, oxygen atom in a box, the 3 lattice vector that we were talking about before, A1, A2, A3, X coordinate, Y coordinate, Z coordinate, number of atoms, position in Cartesian coordinate in the center of the box. And then the last one is the key point. So the key point, like you, in this case, we just use one key point because we just have a single molecule. And you see that here, there is not run.sh file. So in your case, you will need to copy it in your bin folder. In my case, I don't need because I already have in the bin folder. So what you will need to do is like run gen, then I call it test 4.5.3.5. I execute it. Now you see that this run.sh appears, and this is the run file. So this is the file that we need for submitting in Tekla Home, you know? You see, this is the name of the test. This is the direction where the email will go. So that is where you should change and put your username, okay? And what is also important is that you need to change this executable because usually it's good, but in this old version is not good. So you can do that either like using the VI editor. So VI space run.sh. So now you can modify this as if you were in a Microsoft like file. Okay, so you go here. In this case, I try to do things, but nothing really happened, or they happen up because what you need to do, you need to remember to click Y, because Y enable this insert like system, let's say, so that here I can modify things. So here I can, for instance, delete this std and then ask yeah. Okay, now it's a bit too much. Then I just need to type, I type ask and then the 2 point and then, okay, these are too much because it's just like a disloaded system. So the 2 point WQ. So this you need because this is to write and this is to close. So if you do that, then it means that we save the file. And now if you see, is the same as before, but now I modify and I remove this, and now it's VASP, nothing. So now this system is ready to be submitted.
Okay, so can I
Yeah.
stop you a moment? That run.sh, it's a file that it has been appeared when you
When I execute rungen.
Okay, so the command rungen takes the files, the podcast and all those kind of things, and makes sure that
No, yeah, actually it doesn't even take this file. Like you can execute it everywhere you want because this
Okay.
rungen, what it does, and you can check the on script yourself,
okay, yes,
is just to print like this line
okay,
depending on the input that you put.
Okay.
So like if yeah.
just for generating that document.
Exactly.
Okay.
Yeah, tell me. You can. We have any point? Rangen, yeah.
Random test for
Don't write it because all this is they are all in the slide.
There's a program or software.
Huh?
There's a software.
No, it's not a software. This is just a command that you put in your bin folder. So the bin folder is a folder where you can store all the command you want. Okay, and so in this case, like this is a command. So if I do like this, you see these are all command. I mean, these are all command. This is all the content of the command. So what all the file does you see input, name of the system, QID, 4, number of processors, 4, version of VASP, 5.3.5, okay?
And I mean, we use VASP, not VASP STD.
Exactly, and then you need to change VASP underscore STD to VASP. But you will remember that because if you try with VASP STD like this one, the simulation will fail. Okay?
It's wrong.
No, it's not that it's wrong, but that old version of VASP doesn't support this VASP space STD executable. So that is just an internal problem between the two. Okay? So the last two things, you want to visualize your system. Python for VASP space postcard. By doing that, okay.
One.
Yeah, but because I think, I see. Yeah, I mean, it's better that you do it with, yeah, now I know why this is happening. Yeah, okay, this is happening because this postcard is also a bit like, how can I say, not properly written in the sense that you should have the species, okay? I mean, luckily they don't fail because they still work because you also define your species in the pseudo potential, so it's not that important. But I think that the problem why like you cannot use Python for VASP. Okay, now it's again slow. Okay. Come on, okay. Yeah. Okay. Yeah, now it should work. And otherwise do Python for VASP. Okay, no. Then do it on the phone. Well, I do it like that. Because I have all the solution already. So okay. Okay, also it's good to know that for tomorrow that this any desk is not really that effective because then it's really depend on the connection. Okay, so like this. So I just wanted to show, like, it's important that you see the structure mostly on the final system. So don't worry, like, that doesn't work because it's, I mean, it's more important on the concar. Okay, and coming. Okay, now it's already solved. Luckily, in your case will be faster. Okay, yeah, you see, this is the concar. So just look at the concar after you submit the simulation. Okay, this is just to show you. So this is a single oxygen in a box. Coordinate 0, 0, 0. You see that is in the origin, and you see that these are the lateral dimension 8, 8, 8. Okay. So the only thing that you need to do is to visualize that, but visualize directly the concar, avoid the postcard because it's written badly. And the other thing that you can do is to check the VASP run. So the VASP run is also, let's say, the final result. So you can still see the structure, but for instance, you can also go to convergence and you see the energy of your system. In this case, you don't see anything because this is just a single step, okay? You will see like on the answer what steps are, but you can play with that, okay? So for instance, in the case of the ab initio molecular dynamics, if you could be able to check how everything moves. So for instance, if you go to window, you see that this is a water molecule, periodic, okay? And then you can go to control, molecular dynamics, speed, you put 1, play, and you see how like the molecular dynamics is performed. So you see that there is like stretching between like the hydrogen and the oxygen, okay? So all these things, you visualize them after submitting the simulation. And then you go to, if you want, you can go to convergence, you check the energy. So you see, these are all the energy of the system. So you see that depending on the temperature, these are like the steps. This is fluctuating, okay? But you play with that after submitting. So now the last important things let's say after you will copy like that, answer one, not the dot answer that is the one with the solution. After you copy this one, okay. After you do that, I just want to I'll do it later. Like after you copy that, then you submit. So in order to submit means that you open a new terminal. In this case, you do this SSH tecla dot ICQS. It asks my password. You all have your password. Now I am inside Tecla. So now I am inside the supercomputer. Okay. Here is where I can submit the things. So here, if I enter answer one, then I enter 1 oxygen. Here, if I want, I go like, okay, I already have my run, it's okay. I check that I have all my last file, I submit to sub run.sh, enter, your job has been submitted. Then if I want, I can check my job, who start at Dattila. You see that my job is received. It has been submitted on the 9th of September at 11:53 on the QC4, and it's taking like 4%. You see that my, like now we have much more input, well, output than before, because the simulation is like running. Here you see something. So these are the electronic steps, and here you have the final energy of your system. You will check this on the answer, and we can discuss about that on Wednesday, but I really want you to try to figure it out yourself because it's more interesting, let's say. And then here, like if you want, you can also check the out card. So the out card, you can use more if you want. So the out card is basically like the summary of whatever happened. So here is telling you, okay, I take a Incar, I use a pseudo potential POW from 2002. I'm taking a lot of this parameter, and then like I'm doing a lot of things, like I see that there is in the postcard like one atom in a box. I see that there is just one ion, and here you see all the information, but usually you don't open all the time the output because there you have all the information. You just like get the information that you want. So for instance, you can do, if you're interested to get the energy, you can do. Okay, whenever you see strange things, it's just because the computer is losing things. Okay, now, so for instance, you can do this. Now we come. Okay, and so this is to print the energy of your system. Okay, so this is the energy without entropy. This is the energy. Usually we take this one. Okay, but again, we will discuss about this in the following time. The most important things for like tomorrow and mostly for Wednesday is that you copy like the folder that you find in my Tecla home. So this one, you copy all of them. You make sure to have a run.sh file inside. And then after doing that, when you have all the 5 things, you enter Tecla home, you submit them. And after you submit them successfully and you see that they are done, because when they are done, you will not see anything anymore. You see, now if I try to do the same as before, I don't see that there is any job because the job is done, the job is finished. Okay? Then after you have this, then you go back to that folder and okay, and now you check what happened. So you do like Python for VASP concar, and you do what we already did before, you know. So I just move this here so you can see the structures and other things. Okay. Okay. Good. Question?
Yeah, and when we look for the energy W,
Yeah.
W energy, I mean the energy W is the energy without entropy. So the energy without entropy is F or E. I mean
yeah, I understand what you mean.
Because after every calculation, after every round, they will have one F and another
Yeah, but
E.
because you are checking, you are checking the oscillator. You're talking about the oscillator now, I think.
Okay, outcard also have it.
Okay. But wait, I'll show you. Okay.
Okay,
So
I
you
can
see
see
one
yeah.
F. Okay.
Yeah.
So you don't take, never take this energy. I mean, these are the same energy, but the energy you always take from the outcard, and the way that you get the energy, you do like that. Then you have two different type of energy. You see energy without entropy, and maybe I move this one up, and energy for sigma that goes to 0, and we will see next time why you need to take this one. So this is the meaningful value in VASP. Okay, energy for sigma that tends to 0. Okay. So this is the meaningful value for VASP. Okay.
And then, so the F and the E, they don't have any importance.
So the here you mean.
Yeah, I know. I mean, that,
Okay. So the point is that the oscillator
yeah.
is just like a file that is printed to track what is happening. But the meaningful file is the outcard. So like the oscillator, if you just check, I mean, you just check to see if there are problems, you know, if your simulation, for instance, failed, then maybe this file got like cut here, you know, just until the 4, and then you open oscillator to see what happened. But otherwise, you never check the oscillator, or like you don't focus too much on the oscillator, because in the oscillator, the only thing that is telling you is that after 7 electronic steps, so after 7 electronic optimization, then your system got to the first like minimum, is 1F, and you get like different energy, you see, but and actually if you go to oscillator, you see like there is a definition of what these 3 energy are. Okay, so you can check online about that. But I mean, you can check because you're curious, but the only important one is that the energy, the important one is this one. Okay.
Okay, and when we calculate the energy this and this, and
We need to add, yes,
this thing is
excellent, yes, yes.
the energy W.
Excellent, excellent. So this energy for sigma that is equal to 0 is, let's say, the enthalpy. So whenever you want to calculate the gift-free energy, that you need to correct for the temperature and the entropy. But that is not given here. While in Gaussian, they give it, in VASP, no, you need to apply a correction later. So in Gaussian, in VASP, you need to calculate the vibrational frequencies. From there, you extract the entropy, and then you correct for the temperature you have. Okay?
Okay.
So this is a further correction that is not applied here.
So that is exactly the enthalpy.
Yes,
Yes.
yes. In principle, yes. I think that probably for the enthalpy, we should still correct for the 0-point energies, at least in electrocatalysis we do. But let's say like this is the closest you can get from VASP to the enthalpy. Okay, so that, I mean, let's say, to better define it, this is the energy or the electronic energy of your ground state that is the closest to the enthalpy, to the experimental enthalpy.
Okay.
This thing is with entropy or
Without. All these calculations are without. So in
there are 2 words.
Yeah, but you see, like, so energy without entropy, all of them are without entropy. Okay, even if you just define here just because they wanted to save space. So all of them are without. The point is that this one is this energy without entropy for the parameter sigma that goes to 0. Okay, so in the INCAR, we will discuss about that on Wednesday, but in the INCAR, you see that you have this is near equal to 0. That means that you have a Gaussian smearing, and to have a Gaussian smearing means that you have okay, that you have basically like the distribution of okay, this is the DOS, the density of state, let's say, and this is like, these are your electronic state for like the
energy.
for the energy, exactly. And so what is happening, like you see for the Fermi distribution, usually what is happening is you have something like that. I mean, at least at the temperature equal to 0, what you should have is that you have maximum occupancy of your state, and then goes to 0 after you go beyond the Fermi energy. Okay, at least for a meter. And this sigma parameter is since like you see that this transition, so from 1 to 0, like no, this is very bad, but this is a 0, like from 1 to 0 numerically is really bad, because if you solve something numerically, it's really bad to have a discontinuity. What we do, so what this sigma does is to apply a smearing. So what this sigma does is simply that, okay, why now I'm losing? Okay, now, oh, come on, okay. What this sigma does is simply that you have a more continuous like function, so you have something like this. So the sigma, let's say, is this width. I mean, it's a parameter that affects this width. So it's a parameter that kind of rule how continuously your occupation of the electrons goes from 1 to 0. So higher is the sigma, softer you have this transition, but the point is that in DFT, usually we are calculating at t equal to 0.
Yeah.
So the most correct one will be instead to have the real system like that, to have it going from 1 to 0. But you cannot go from 1 to 0 because this will be numerically a nightmare to solve it. So you apply a sigma to make it soft. But then since the correct one is the red shape, then you take sigma that goes to 0.
I mean,
Okay.
just like this.
Exactly. I mean, you take the calculation applying a softer transition, but then after that, you apply a filter to get from that value of the energy for the soft transition the previous one. So that's the reason why you see sigma equal to 0, because the sigma equal to 0 simply take, let's say, the energy is calculated for the soft transition, but then you apply something on top of this energy and you get an approximation of the energy of the real system and should be. So with this very harsh transition that you cannot calculate numerically because the system will fail. Okay?
And we don't need to use the F and E in anything.
No, I mean, the only thing that is important is this value, okay? So you take this one, and this is the only important value for you. Okay, full stop, okay? Good, I think it's 12:05, so if there are no more questions, you can all rest, and we see each other tomorrow at 10. And remember, tomorrow, focus on the question. If you have questions, maybe talk between you four, so that you know you can ask meaningful questions. You don't repeat your own question, okay?
I think tomorrow is at 12. I'm right.
Yeah, I think it's okay.
Okay.
Sorry, guys. Yeah, because it's taken. Yeah. No, I think Rick is right because
tomorrow
we,
is the,
yeah,
is the special day.
yeah, we needed to change. I mean, let's just check. Okay. So tomorrow, let's see. Yes, tomorrow it's at 12. Yes.
Okay.
Tomorrow is from 12 to 1. Okay.
Okay.
Right before lunch.
Okay.
Good.
Perfect.
Okay. Good. Marian, do you want to check this?
Yes, please.
Okay. Then I stop sharing. But I stop recording actually. Okay. And I also close a bit all the things. Okay.